that you get. So it's also good to be here for this other reason, definitely. Right, so just to establish the notation that I'm going to be using, just a quick introduction to things that we all know about. So we're cosmologists. We want to measure these kinds of parameters that parameterize our background cosmology and the perturbations. In order to do that, one of the arguably best ways of doing that would be through the density field. So by looking at the statistics of the density fluctuations under the assumption that they're Gaussian, most of the information is then going to come from the variance of these perturbations, which is the power spectrum. But we don't have direct access to this quantity. What we may have direct access to is observable. So things. The thing that we observe in our telescopes is light, basically coming at different wavelengths and from different positions in the sky. So we mostly measure proxies of the density inhomogeneities in the form of CMB temperature and polarization fluctuations, the galaxy density field, galaxy shapes, Lyman alpha, 21 centimeters, and all that. And even this is something that we don't have direct access to. What we have direct access to is the observations of these quantities through an instrument, which means that on top of the true signal, we have noise and we have systematics. Trying to go from here to here is essentially like trying to resolve a large number of nonlinear stochastic equations with a number and with one equation per observable that we have, basically. So we have more observables, then we have better chances of trying to solve for these unknown quantities. And in solving this system of equations, we have to worry about systematics, and there's systematics in every step of this process in terms of instrumental systematics and observational systematics, astrophysical systematics, and theoretical systematics. Because this is an LSST conference, I have to have an LSST slide. So you all know this. The particular one thing that is particularly good about LSST is that it's not just going to focus on one observable. We're going to be able to focus at least on 5 different observables. So we're going to have a lot of equations that we can use to solve for the cosmological parameters. This is the latest image that I have of the LSST, which we received recently with the secondary mirror arriving at the site. So that's very exciting. And as Chiwe was saying yesterday, things are going really, really fast, and it's very scary that this is already almost built. Okay. So ideally, this is what we would like to do. We have some observable, and here I've taken some density field from the, I think this is the year 1 DES density field of galaxies. So we have some observable. In this case, it could be basically all the galaxies in our catalog. That could be our data set. And then we want to evaluate this probability distribution of the cosmological parameters given our data. And we had to do that. Some magic needs to happen in this box so that we get final constraints on cosmological parameters. So in the most optimistic scenario, where we want to go directly from a raw observable, so all the quantities at the catalog level associated with our galaxies, we essentially need to sample this probability distribution, which takes a number of steps, which I basically mentioned before. So in order to be able to relate cosmological parameters to our observations, we need to be able to relate the cosmological parameters to the power spectrum. So we need a cosmological model of some sort. We need a structure formation model that tells us what is the statistics of the density field, giving a power spectrum or something else. We need an astrophysical model that tells us what the relationship between the matter fluctuations and our proxies of those matter fluctuations is. And we need to be able to model our instrument in order to relate the observations to the signal. And in all of these, there are systematics that we also need to marginalize over. So theoretical systematics, nonlinearities, baryonic effects, etc. Astrophysical systematics, galaxy biases, intrinsic alignments, mass observable relations for clusters, and many others. And instrumental systematics, so photosees, depth variations, shape measurements, and lots of other things. So ideally, we would like to be able to sample this hugely multidimensional probability distribution and to marginalize over all the things that we don't care about. But this, doing this would be, it is computationally very, very demanding. It is something that we should try to do eventually because this is manifestly the optimal way of getting cosmological constraints, but it's computationally very, very hard. And some people are already working along this line. There's this Borg code that essentially implements methods to model each of these probability distributions and marginalize very quickly over them. This is a great approach, and I think eventually we'll aim for that, but it's computationally extremely demanding and very, very tricky. So instead of doing that, what we usually do is we make approximations. And the usual approximation is to implement a simplified two-point pipeline. So the idea here is that instead of using all of your data at the catalog level as your data vector that goes into your likelihood directly, you first reduce the dimensionality of your data vector by using only two-point functions. So essentially, and then you include all the cross correlations between different tracers of the density field. So the bad thing about this is that then you're disregarding the information coming from any higher order moments. However, if your observables are close to Gaussian, then maybe there's not that much information on those higher order moments. Because the two-point functions effectively are averages over identical modes, statistically speaking. So for example, you use statistical isotropy to average over equivalent directions in the sky and things like that. Effectively, each of these two-point functions is an average over many modes. And if the number of modes is high enough, then the central limit theorem tells you that the statistics of your two-point function should be very close to Gaussian, which means that then your likelihood becomes very simple once you have measured these two-point functions. And reducing the dimensionality of the data vector is quite important, as I will discuss in another part of my talk. So once you have computed your two-point functions, then what you do is you model everything at the summary statistic level. So you just model the effect of astrophysical systematics, theoretical systematics, instrumental systematics at the two-point function level. And this is arguably less optimal in terms of systematics marginalization because you have fewer degrees of in order to constrain your systematic parameters. But maybe you can actually summarize all of these systematic effects into a smaller number of effective nuisance parameters. And this approach is possibly less sensitive to modeling uncertainties. And this is something that we can talk about later. Okay, so very briefly, the kind of idea in everyone's mind, so in anyone who has worked, for example, in DES or HSC or any photometric redshift survey, is that photosys are very complicated. So what you do is you forget about any radial information. You just bunch up galaxies into photometric redshift bins or some kind of samples. And then you project all of these observables onto the sphere. So you have a two-dimensional thing. And then you compute all the possible angular two-point cross correlations between all your different redshift bins. And use all of them, or at least some of them, in order to get cosmological parameters. And this is an example of the lensing power spectrum measured by HSC. So I'm alternating HSC and DES plots so that no one gets angry. Right. So a very complicated slide here that I'm not going to describe in detail. So this is the TX pipeline that we're developing in LSST, which Chi-Wei already talked about yesterday. So this is a bunch of steps that you need to go through in order to go from the kind of data management level catalog to a two-point function. So there's a number of steps. You estimate photosys, you divide your sample into the best samples that you want. So what are your lenses, your lens sample, your sources sample. You map your survey geometry in different systematics that you want to marginalize over. Estimate two-point functions, you estimate redshift distributions in order to be able to model these two-point functions, and somehow, through magic, you estimate the covariance matrix. Once you have a two-point function and a covariance matrix, then you put it in a Gaussian likelihood like this. So your data is this set of two-point functions, some theory prediction for those, a covariance matrix, and that gives you a probability for your data given your theory. So I'm going to talk about 3 steps in this kind of pipeline, and about part of the work that I've done in these different parts. So I'm going to talk about estimating two-point functions, about things related to covariance matrices, not necessarily to estimating them, and about the theory coming up with your prediction. So the first paper I'm going to talk about is this paper we put out in September together with Javi Sanchez and Anges Lozar here, where we basically, this is basically a code paper, so it's a paper that presents a code and that we believe is going to be useful for the community. So let me tell you exactly what this is about. So the code I'm going to be talking about is called Namaster. It's basically a code that computes angular power spectra, so which is essentially the 2-point function of the harmonic coefficients of whatever quantity you have in the sky. So why do you want to compute spectra rather than correlation functions, which seems to be what the majority of large-scale structure surveys have done so far? So there's different reasons. Power spectra, so anything in Fourier space in general is more closely connected to our theory. We seem to understand better where the difference is between small scales that we don't understand and large scales that we do understand in Fourier space rather than in configuration space. So you can do k-cuts that have a clear interpretation in Fourier space, and you don't have to worry about what happens through a Hankel transform that mixes all those scales into real space. So that's one reason. The covariance matrix, so because of statistical isotropy, anything that you do in Fourier space is always going to be more diagonal than things in real space. So your covariance matrix is always a lot more diagonal in Fourier space than real space. So that means that once you have a power spectrum, a theory line, and some error bars, you can almost do a chi-square by I. If the line doesn't go through the point and error bars in most of the points, then the chi-square is going to be bad, and you can very easily say whether it's going wrong. And that's not necessarily the case for correlation functions. And arguably, you're going to need a fewer number of mocks in order to estimate the corresponding covariance matrix in a way that it can be inverted and not give you issues with ill-conditioned covariance matrices and things like that. If you want to compute a power spectrum, it scales with n to the power of 3 halves, where n is the number of pixels that you have in the sky. A brute force 2-point function scales as n to the power of 2, where n is the number of galaxies that you have. It can be sped up using tree codes, but still it's computationally demanding very often. So there's also some advantages in terms of computational speed if you use power spectra. Okay, so this is just the sales point of why you should be computing power spectra instead of 2-point functions, although there are pros and cons to both of them. So we've known how to optimally compute 2-point power spectra since the 90s, and I've forgotten to add a citation here, but basically the first paper that initiated all of that was by Max Tegmark. So we know that if we want to compute a power spectrum, what we should do is we should take our data. So think of your data as being a map on the sky with different pixels. So this is a vector of pixels. You inverse variance weight it. So this is the covariance matrix of your data. You inverse variance weight your data. This is effectively an operator that Fourier transforms your map in this direction and in this other direction, and you're effectively squaring the Fourier transforms of your inverse variance weighted map. Once you do that, you have to worry about two things. First, your data probably has not only signal, but also noise. So your noise is going to give you an extra kind of noise bias that you have to correct for. And because you have an incomplete sky, you have the different modes are going to be coupled. And there's a mode coupling matrix that you need to invert in order to get the unbiased So this is a very complicated equation that becomes extremely simple if you have a full sky and homogeneous survey. In that case, effectively the recipe is that you take your map of whatever quantity you're mapping, you Fourier transform it or harmonic transform it, you square it, and then you sum over the azimuthal degrees of freedom, which are all equivalent, and then you get an estimate for your power spectrum. So this is extremely simple, just Fourier transform, square, and average. In any realistic scenario, if you do that, you will get a biased estimator of the power spectrum. If you want to use the optimal quadratic estimator, which is the name of this estimator here, in order to compute power spectra, you have two issues. First, you need to invert the covariance matrix. This is a number of pixels by number of pixels matrix. So this inversion, if you're not very smart, is going to be a number of pixels to the power of 3 operation, and that becomes extremely slow. And that's not the worst of it. The worst of it is actually computing this mode coupling matrix that can take forever if you have a very high angular resolution, so a large number of pixels. So this can be extremely slow, and there's so what the code talks about here is an approximation to implement this method. So this approximation is what we call the pseudo-CL estimator, or what people call the pseudo-CL estimator. So in short, essentially what you do in a pseudo-CL estimator is you do things wrong to begin with, and then you correct for the fact that you shouldn't have done things wrong. So doing things wrong means effectively that you do on your incomplete sky what you would do in a full sky. So you Fourier transform it, you square it, and you sum over m. Forgetting about the fact that you have a mask and all of that. So before I move on, so a mask basically it's telling you the weight that you want to apply to different pixels in the sky. Minimally, it should be a 0-1 mask that tells you this bunch of pixels in the sky are completely dominated by, I don't know, like there's a star there that is screwing all over my my data, and I don't like it, so I mask it out. But more generally, what you can use a mask for is basically to upweight or downweight different pixels in the sky based on, for example, the noise level of the different parts of the sky. So optimally speaking, it should be a kind of inverse variance weighting thing that assumes that all the different points in the sky are uncorrelated. So once you mask your sky, you Fourier transform your sky, and then square it and average over m, and then eventually you figure out the mode coupling induced by this set of operations and correct for that. And the fact is that figuring out this mode coupling matrix, which I said is extremely slow in the optimal case, in this less optimal case, it can be done analytically. So it's basically a very fast operation that you can do in an n pix to the power of 3/2 time. So remember, in the previous case, it was n pix to the power of 3, which is intractable. This is a lot more tractable. Okay, so that's what the pseudo-CL estimator does. Let's see whether or not it's actually a good idea to do that. So when is the pseudo-CL estimator? So you can think about the pseudo-CL estimator in two different ways. The first one, which is what I said before, is effectively doing things wrong and then correcting for that. The second one is that what you're doing is you're approximating your covariance matrix that enters the optimal quadratic estimator. You're approximating it as being diagonal. So instead of computing a full matrix and then inverting it, what you do is you just multiply each pixel in the sky, but by the inverse variance of that, which is your mask. So the pseudo-CL estimator essentially is the same as the optimal quadratic estimator, as long as this approximation that the covariance matrix is diagonal, as long as that approximation holds. And that's going to hold if you have full sky data. So both estimators reduce to the same thing if you have full sky data. But more importantly, if you have a flat underlying kind of power spectrum, or if you're dominated by noise, in which case the power spectrum is usually going to be pretty flat. So if you have basically if the power spectrum of your signal is something that doesn't vary with scale really, really strongly, then the pseudo-CL estimator is going to give you basically optimal error bars without having to worry about the whole inversion of a covariance matrix thing. So if we look at the power spectrum, the typical power spectrum of galaxy clustering, for example, this is, for example, from the CMASS galaxy sample from BOSS. You can see that it goes down by about 1 decade, less than 1 decade in about 2 decades. So it is definitely not completely flat, but it doesn't vary with scale as strongly as, for example, the CMB power spectrum does. So if you look at the CMB power spectrum at very low L, it goes down by almost 3 decades in about 1 decade. So it's a lot steeper. So if you try to use the pseudo-CL estimator for the CMB temperature power spectrum, you will get a power spectrum, but the error bars of that will be very suboptimal. However, if you use it for large scale structure, or in general for any power spectrum that is sufficiently flat, then the pseudo-CL does the job without having to worry about computational issues. Okay. So that's with what we've implemented in this code. It's called Master. It's a public code. It's been developed within LSST, within the Dark Energy Science Collaboration in LSST. It's very thoroughly documented, and it's computationally efficient. You can call it from Python in the same way that you would call like HillPy or any other module that you use every day. With put a lot of effort into, providing lots of examples on how to use the different pieces of functionality of the code. So we think it can be a useful tool. So let me tell you a little bit about what these different functionalities are. Because this method has been around for a while, there's other codes that do kind of pseudo-CL power spectra. So why would we bother write another code that does pseudo-CL power spectra? The reason is that these codes, not all of them are, so none of these codes satisfy all the different, the following set of requirements that we have for what we would like to have for LSST. So none of them have a wide range of convenience features that I will talk about in a second. So basically some of these codes implement some things and some other codes implement other things, but none of them have the full set of functionality that we would like to have. We have we would like for the code to be completely and thoroughly validated, and that is true for some of these codes. It's not necessarily true for all the codes. It should be continuously supported and well documented, and that's not true for some of the codes. And it should be very easy to install and use and all that, and that's not true for many of these codes. Right. So let me tell you basically about the different things that we have implemented in the code. So it can compute pseudo-CL estimators, and it essentially can compute any cross power spectrum between any two quantities that you give it. So it's capable of doing things in the full spherical, the full sky kind of sense, the curved sky, no approximations sky, and in the flat sky approximation, which is very useful if you have very small patches in the sky, because things are a lot faster and more efficient in that case. It can cross-correlate spin 0 and spin 2 quantities, so things like density or things like shear, it can do. And it can do any cross-correlation between them as well. And it has these bells and whistles that are actually quite useful, which is mostly these two things called mode deprojection and EB mode purification. So I'm going to describe these two things very briefly, and then I'll move on. So first on this mode deprojection thing. So in the works of Anges Lozar, one of the co-authors, mode deprojection is the greatest thing since sliced bread. He's very excited about mode deprojection. So the idea here is, so as I said at the beginning, if you've measured whatever, let's think of the density field, for example, in different pixels in the sky, and you know that a bunch of pixels are completely affected by, a star that is messing up your observations there, then you basically mask out all those pixels. So that's what you do when you mask. Mode deprojection is essentially a generalization of that idea. Where instead of doing like a complete masking of a region in the sky, what you do is you remove from your data any modes that look like a contaminant that you think is contaminating your data. So for concreteness, let's think of the usual thing, which is dust. So we have galactic dust. Galactic dust is going to affect the effective number density of objects that we observe. But we know what galactic dust looks like in the sky because we have maps of dust from Planck and many other experiments. So if you know what the galactic dust looks like, you can remove from your data any modes that look like galactic dust. So the idea is if you have your observed data is essentially the true underlying signal plus a linear combination of different templates corresponding to different systematic maps of the sky multiplied by some unknown linear parameters. The idea is that you can try to remove all the modes in your data that look like any of these set of templates, contaminant templates. So if you go through the math of what this means for the pseudo-CL estimator, essentially this means that you first infer what the best fit parameter, the best fit value is for these linear components. Then you use that best fit value to to remove these components from your data. And then essentially if you have removed a number of from your data, if you compute the power spectrum, then you have to account for the fact that you have missing modes in your data. So at the end of the day, you need to you basically compute the standard pseudo-CL estimator, and then you have to correct for the fact that you have missing modes, and this can all be done as most things can for the pseudo-CL. It can be done analytically. It's actually a very fast operation. So if you want to know more mode deprojection, go to any of these two papers or to the original, the Namaster paper, and you can see the whole maths of it there. This is extremely useful for large-scale structure experiments. We have a large number of systematics that we don't necessarily know exactly how they affect our data, but we know that they affect them in one way or another. So I mentioned dust, but you have things, you have lots of other things like PSF, variations, you have depth fluctuations, you have air mass, you have seeing, lots of different things that you probably want to remove from your data straight away and not worry about them. So this can be extremely useful for large-scale structure in general. And it's manifestly optimal in the sense that you're doing things at the map level, so you're not correcting things at the final power spectrum level. You're removing everything at the map level where you have phase information and all that. So it gives you the best possible error bars that you could get and automatically marginalizing over these systematics. Okay, so that's for mode deprojection. The other thing that is implemented in the code is this EB purification, which maybe is not so popular in the large-scale structure world, but it's actually very, very useful in CMB. So the idea is as follows. If you have a sky mass, so if your sky is basically not complete, but it has holes and edges, then if you have a sky, for example, that only has E modes, you compute the E and B modes of the masked sky, you're going to get a lot of E modes because your sky had E modes to begin with. But also around the edges of your mask, you're going to get spurious B modes that are not real. They're just caused by the fact that you have a mask. So that's fine if you push this kind of data through the pseudo-CL estimator. The pseudo-CL estimator is going to be able to deal with these spurious B modes and it's going to correct for them. But the problem with the standard pseudo-CL approximation is that it does that in the final stage. So basically it computes, as I say, it computes the Fourier transform squares averages over M, and then it realizes, wait, but because of the mask I have EB mode mixing, so I have to subtract some extra stuff, and it does it automatically. But the thing is that it's doing it at the power spectrum level, so at the 2-point function level. So if you have an E mode, if your E modes are much larger than your B modes, then because you're only subtracting the bias in the power spectrum at the very end, your E modes are going to contribute to the variance of your power spectrum estimator. And if you have very large E modes, that means that the final error bars on your power spectrum are going to be very, very large. So you want to be able to remove or to get rid of this E to B mixing due to the mask. You want to be able to do that at the map level in order to reduce your final error bars. So in order to do that, there's this method called EB purification, and essentially what that does is analytically it figures out which of the modes are ambiguous, so which of the modes could either be E or B, and then it removes all of those modes automatically. So if essentially you're removing modes from your data, so you're losing some sensitivity, but because you're losing the modes that will give you the highest variance to your final estimator, you actually get much better error bars. Just a show of that, this is from the master paper from part of our validation. These are the error bars on the BB power spectrum for a kind of CMB experiment. These are the error bars. So if you focus on the solid lines, that's for the BB power spectrum. The blue line would be if you do the standard pseudo-CL. The red one is if you do a pure B analysis. So if you purify your B modes. And then in that case, you can see that you get more than 2 orders of magnitude improvement on the error bars, especially on large scale. So this is very useful, in particular for future CMB mode searches. So that's also in the code. So because I'm not going to have time to talk about everything that I want to talk about, I'm not going to be very thorough at telling you about the validation of the code and all that. We have a validation suite that implements realistically the different kinds of things that you need to worry about in a large-scale structure experiment and in a future CMB B mode experiment. We have a set of simulations that we use to validate our code. We make sure that we can recover unbiased estimates of the power spectrum and then showcase how important, for example, deprojection, mode deprojection is in order to not get biased power spectra. And then numerically, we check that we can recover true power spectra by looking at the final chi-square distributions of the different simulations, zero bias, at least not detectable bias. And final slide on this. So the code is out there. It's not just a code. It has been used to produce results from forecasts for the Simons Observatory to measurements of the CMB lensing cross quasars and DLA's signal in BOSS. The measurement of the 2-point clustering in the year 1 data from the ES by actually some people in the audience. We're using it on a paper that I'm going to talk about in a second, where we look at the lensing of the CFHTLens dataset for one particular purpose that I'll mention later. And we're also using it in the analysis, in the clustering analysis of HSC, which is a project currently going on in the large-scale structure working group in LSST. So it has and it can be used on data, and I think it's extremely easy to use. So I would encourage you to go ahead and use it if you think it's useful. Okay, so that's all I have on this PR stunt. Now let me move on now to covariance matrices, and in particular in the context of data compression. So this is a couple of projects. The latest of one we're finishing up now with Emilio Bellini, who is a postdoc at Oxford, a very smart guy. So what do we mean by data compression? So if we wanted to do this ideal analysis where we just take data at the catalog level and then we push it through a likelihood, we would have to worry about a lot of data, right? We would have a catalog with billions of objects, and for each object, at the very least, we're going to have about 5 quantities that we need to that we need to use in our analysis. So that's many billions of elements of your data vector. In a 2-point function analysis, what we do is we compress all of that into a number of cross correlations between different subsamples of your data. So that's probably going to be a huge amount of data compression. So, but what is the actual number of final data points that we have? What is it? So if we take an ideal kind of LSST sample in the future, let's say that we have 10 redshift bins for our sources and 10 redshift bins for our lenses, and we measure the power spectrum for each of those cross correlations in about 15 angular bins. For simplicity, I'm assuming that you use all the different cross correlations. In that case, your final data vector is going to have about 3,000 data points. Okay, so that's pretty good. We have like 3 million, a factor of 3 million in terms of data compression. If we like going from the original ideal data vector to the summary statistic. And what we've done in order to do that is we've selected the most informative parts of our data. In this case, the 2-point functions, and we've averaged over all the equivalent modes. In this case, we're using, for example, statistical isotropy in order to not worry about equivalent modes. Now we have a 3,000 element data vector that we need to compute the covariance matrix for, however. So how do we compute covariance matrices? There's different ways. I'm just going to mention 3 of them. So one is jackknife or bootstrapping, where you basically divide your own data into different smaller samples, and you use all of those samples to compute a covariance matrix. Another way of getting samples is using mock catalogs, using fast methods or actually embodied simulations, and there's many ways of doing that. And some of you guys here work on some of that. Some of those. In general, you're going to want to have a number of samples that is larger than 10 times the size of your data vector in order to get a covariance matrix that is more or less converged and that you can invert. So that means you're going to need of the order of 30,000 simulations, let's say, for LSST. That should cover the volume of LSST if you want to go this way. And that, maybe we can do that, but it's definitely a non-negligible amount of computation that we need to do. Another way of going about it is computing an analytical covariance matrix. So I'm not going to go through the equations. It's just to show that there's a lot of equations that you have to implement in order to compute an analytical covariance matrix. You have to worry about the Gaussian disconnected part. This is a mistake. It should be disconnected part. And this is all taken from Elizabeth's paper. The supersample covariance, all other non-Gaussian connected parts, if you need to worry about them. Then, once you have something for the covariance matrix for the power spectrum, then you have to, if you're doing things in real space, you have to do a double Hankel transform to go to correlation functions. And probably at some point you have to worry about survey geometry, whether or not that's affecting any of these parts of your covariance matrix. And the thing is that the computation then scales very bad, because essentially you have to do that for the square of the number of data points that you have. So for example, with the number of bins, it's going to scale pretty bad. In terms of survey geometry, by the way, Namaster is able to do some of these, and we're working on implementing more of that. So hopefully it can be useful as well for that. But anyway, so all of these different methods of computing a covariance matrix would benefit from reducing the size of the data vector. The computational complexity of all of these increases with the number of data vector elements. So if we can compress further, then it will make our lives a lot easier, regardless of how we want to compute the covariance matrix. So the question is whether or not we can actually compress. So let's take one example, which is cosmic shear. So in cosmic shear, so if we look at the expression for the signal power spectrum, in cosmic shear, it's essentially some integral along the line of sight of 2 window functions times the power spectrum. And these window functions are some integral over the redshift distribution of our different redshift bins. So we take, for example, the CFHTLens analysis that Chi-Wei was mentioning yesterday. We have 7 redshift bins, for example, like this. If we look at what these window functions look like, essentially it's an integral along the line of sight, and they look like this, which makes sense in the sense that if you look at this redshift bin here, the lensing that is causing the shear in these galaxies is going to be very, very correlated with the lensing that is causing the shear in these other galaxies, because it's basically caused by all the intervening dark matter fluctuations between these redshifts and redshift 0. So basically, the signal between different redshift bins is going to be very correlated. And so if you have large correlations between data points, that means that you have fewer independent degrees of freedom than that you would think eventually. So which basically means that you can always compress things further. So compressing, or actually manifestly the way of compressing things further in the most optimal way is what people call the Karhunen-Loeve transform. And this is a lot of statistical lingo that I'm not going to bore you with. But essentially, this thing called the Karhunen-Loeve transform is a set of mathematical operations that you have to go through in order to select from your data, which is this X here, the linear combinations of your data that contain the maximum amount of information about a given parameter that you care about, which here in general I've called theta. So in order to, so let's think of our data as, for example, being different maps of the shear at different redshifts. Okay. So this would be a linear combination of all of those maps that contains the maximum amount of information about a given parameter. So in order to come up with this linear combination, with these linear coefficients, you have to solve a generalized eigenvalue equation that involves the covariance matrix of your data. So if our data was maps of the sky, this is essentially either the 2-point correlation function or the power spectrum if we're working in real space or Fourier space. And you may want to do this for each parameter that you want to constrain. But a more something that is a lot simpler than doing this for each parameter is to do it for one parameter that probably enhances the final constraints on any other parameter, which is the overall amplitude of your signal. Any questions?
I was wondering whether this is really principal component analysis.
Right. So component analysis doesn't worry about which part of your data informs you the most about a given parameter. It worries only about giving you independent degrees of freedom, but it doesn't tell you which of these degrees of freedom contains most of the information about one parameter or another.
If you order by eigenvalues?
Sorry?
If you order by eigenvalues?
You can see that it will not give you, so that ordering will not give you the maximum amount of information on whatever parameter you want to. So Karhunen-Loeve transform, the Karhunen-Loeve transform effectively is an extra operation on the PCA that combines the principal components into the components that tell you the most about a given parameter. So they're not exactly the same thing, but they are related. Right, so if you optimize the amount of information on the amplitude of your signal, then this generalized eigenvalue equation becomes a bit simpler, and then you can solve this where here's S is the covariance of your signal. So if we think in, yeah.
But then you have to parameterize the model.
Yes, you need, yeah.
So then it has the disadvantage that if you have some extra parameters you didn't think about, right? This might not be able to.
Yeah, so you always need a model. So you need models for all of these things in order to come up with the best possible set of linear combinations. As long as that model is close to the reality, this will do a good job at getting you the most informative modes. It's not going to give you any biases or anything like that. So as long as you have a good model, it's going to give you the best possible.
Does bias you towards the model that?
No. You can think. Sorry. So you can think of, once you have chosen a model, you can think of these numbers as being just some fixed numbers, right, that you account for.
Sorry, can we think about it as the principal component when you vary one parameter? So marginalizing over all of the parameters except sorry, marginalizing over the particular parameter that you're considering. That's the principal component. And if you order them by eigenvalues.
Maybe. I don't know. I would need to go through the math to see if that's the case or not. Yeah.
So I guess the difference between the PCA and Karhunen-Loeve is that the Karhunen-Loeve, you first pre-whiten the data, so you kind of have a signal-to-noise ratio, which is what you're actually maximizing. The principal component analysis, I don't think you do that.
That is completely true for this particular case where you maximize the amplitude of your signal. That is true. Yes. So once you have chosen a cosmological model, this is just a set of values and numbers that don't know anything about cosmology. It's just that they are the linear combinations that should probably contain the most information on your cosmology, but it doesn't bias you towards that cosmology.
But I was just meaning that you could have a different cosmology, which is different parameter.
Yep.
And in this setup, the signal to noise of this parameter will be very low, and then you don't see it. They're not biasing, it's just that you're not maximizing that signal to noise.
So this is just splitting your data into different linear combinations. So you're not losing information or adding information or anything, and you're not. So the idea at the end of the day is you're going to throw out some of these modes, right? If the model that you have used is sufficiently close to reality, then those modes will not contain a lot of information. If it differs, then that means that the final error bars are going to be worse than you would have thought. But it's not going to bias the constraint. Okay. I mean, if you go through the math, there's no bias or anything that it gives you. It's just a way of trying to figure out what are the most informative parts of your data. Okay. So I'm gonna go a bit quicker. So one simple example is if we look at one particular observable, which is galaxy clustering, in a very simplified scenario, which is what happens if you have spectroscopic redshifts. Okay. So in this case, you could think of your data as being the galaxy over density in infinitesimally small redshift bins because you have spectroscopic redshifts, so you can always do that. Then the covariance matrix will be all the possible cross power spectra between all the different bins, and your noise is basically some shot noise flat power spectrum. And you can show, you can prove that analytically, basically the solution to the Karhunen-Loeve decomposition is that your linear component, your linear coefficients are going to be basically the spherical Bessel functions, which means that the Karhunen-Loeve transform is effectively the harmonic Bessel transform, which is a very convoluted way of saying a Fourier transform. And that the covariance of the resulting Karhunen-Loeve eigenmodes is effectively the 3D power spectrum. So the Karhunen-Loeve is telling you that the best way to analyze your data is to just Fourier transform it if you have spectroscopic redshifts, is to Fourier transform it and then compute the 3D power spectrum of your data, which is what you do in spectroscopic surveys. So the question is, what is the equivalent of a power spectrum analysis for a photometric survey? And so the next example would be, can we do this for cosmic shear? So if you do this for cosmic shear, if you take something like what LSST would look like, you can show that the first 3 Karhunen-Loeve modes are going to contain most of the information. They're going to be signal dominated, and everything after that is completely noise dominated. So you can try to see how much information you can recover from these 3 modes. And effectively, if you use 1, 2, and 3 modes, when you get to 3 modes, you recover the same cosmological constraints that you would get on any set of parameters. This is just one example of 2 parameters that you would get if you used all of your data. So this is, and as I just to remind you that formally speaking, it's not just nice in terms of data compression, but from an aesthetic point of view, I like it because it's telling you what is the kind of the analog of a power spectrum of a P of K analysis when you have photometric redshifts, and in this particular case. Right, so this is all kind of forecasts that we did in the initial paper. Then what we're doing now is actually applying this to a real world scenario and seeing how well it actually performs in that case. So we're looking at the CFHTLens data, which is pretty old, but the reason why we chose CFHTLens is that people have done 3D data compression exercises on this data before. So we took the latest analysis from Shahab Yudaki in 2016, which is the same analysis that Chiwei was talking about yesterday. So that uses 7 different tomographic bins. These are the power spectra that we measure in all those redshift beams, which I showed before. So if you look at the size of the data vector that they use, because it's in real space, you have psi plus and psi minus measured in a bunch of bins, and you have all the cross correlations, you have about 280 elements. You can do the Karhunen-Loeve decomposition, and this is a plot that shows the Karhunen-Loeve eigenmodes as a function of redshift for different L's. So the different shadings of each color are the different L's. So something that is pretty nice about cosmic shear, which seems to be quite general, so we've seen this regardless of what kind of sample we look at, is that there is some scale dependence, so there's some dependence with L, but only at the very higher L's, and as soon as you get to L equals something like 100 or something like that, or even less than that, then all the eigenmodes collapse to the same kind of function of redshift, which means that if you forget about scale dependence, it's probably a good approximation, and you can think of these Karhunen-Loeve coefficients as just being a redshift-dependent weight that you apply to your galaxies, which makes it a lot easier to analyze. And so the final preliminary results that we're getting are this here. So these are constraints on S8 and omega m using this. So the black contours are the original constraints got in the Judaki et al. Analysis that uses, as I said, 280 data points. The blue ones are what you get if you use the two principal from Karhunen-Loeve modes. So you're only using two modes, and the green ones is if you use those two modes and you even forget about the cross correlation between those two modes. So you only use the alpha correlation, which is in principle what you should do, because they are, at least at the maximum likelihood of your data, they are actually uncorrelated. So you basically are able to recover the same constraining power that you have with the full data vector, which means that just using two modes is enough, and that gives you a compression factor of the order of 20 to 30, depending on which of these two points you want to use. And that means that effectively you will need a factor of 30 fewer simulations if you need to compute a this, or you will need to compute an analytical covariance matrix factor of 30 squared times less than if you used it for the full data vector. So I think this is kind of interesting. There's many applications of the Karhunen-Loeve transform that people have proposed and that we mentioned in our paper. So if you want to go there and see other things that you can use it for, go there. There's other approaches that are a lot more extreme. So these are papers that are quite interesting by Justin Olseng. If you want to have a read of them, the idea is that at the end of the day, you just use one summary statistic, so one single number for each free parameter that you have in your model. So if we're thinking about just lambda sitting, it would be 6 numbers that you have to compute a covariance matrix for, or evaluate the likelihood for somehow. So this can be very advantageous for many reasons, and it also has some caveats, but I think it's also a promising approach. So go there if you want to know more about that. Right, so I've talked about covariances a little bit. I've talked about two-point functions, and the last thing I wanted to talk about is the theory computation. So as Chief mentioned, there's a paper came out this Monday on the core cosmology library, which is another piece of code that has been developed within LSST to compute theory predictions for our observables. This is a project with exactly 30 people in the author list. The person that has led this effort is Elisa Chisari. She's done a tremendous job. She's one of the postdocs in Oxford. And other people involved is myself. There's Elizabeth, who's also in the audience. Tom is also in the audience. I don't think I've missed anyone else from the audience, but if I have, I'm sorry. Good. Right. Right. So eventually we want to evaluate this likelihood. We need a theory vector, and having accurate models for this theory vector is essential. And when we say accurate, they need to be they need to have an accuracy that is significantly higher than the statistical power in our data. So the errors on this have to be much smaller than the diagonal of the covariance matrix, essentially. And since the statistical power of LSST will be really awesome, then that puts very stringent constraints on how inaccurate we can be when we compute the theory. So we have some requirements for a theory library in LSST that we need to fulfill. It needs to be accurate. It needs to be robust in the sense that it's not that just numerically it gives you some numbers and those numbers are accurate. It means that they have to be the actual numbers. So that means we need a thorough code validation that tells you that whatever comes out of this library is completely correct. It needs to be flexible in the sense that we will want to implement different models, and we want to be able to do that sufficiently quick, and to absorb different kind of systematic models for systematic parameters and things like that. And also it needs to perform numerically sufficiently well so that we can do Monte Carlo in a finite amount of time. So again, a piece of code, it's on GitHub, it's free, it's developed within LSST, within Desk. It's fully documented, and there's an official version 1 release that came with the paper that I would encourage you to use. Again, we've put a lot of effort in making lots of examples to showcase how you can use the library. So it should be very easy to use. I think one of the nice aspects of this project has been the very strict code validation that we have followed in order to develop the library. So the requirements that we have, for example, are that all calculations, so any functionality that we have in the library, these are calculations that have been performed with by at least a different independent code. And then whatever comes out of CCL has to agree with whatever comes out of other codes with either well-motivated or crazily stringent requirements in terms of accuracy. We keep these predictions from other codes as benchmarks, and then we automatically compare CCL against the benchmarks whenever there's any new addition to the code to make sure that we haven't messed up previous iterations of the code. And then on top of that, there's unit tests for other functionalities such as error passing and things like that. So just to showcase one example, this is what you get for power spectra, which is the part of the code that I was most involved with. So this is the error compared to the benchmarks that we have as a function of as a ratio of the error bars that you would expect. These are purely cosmic variance errors for different observables. So galaxy CMB lensing, galaxy, shear CMB lensing, and we have all other kinds of combinations of that. And we're always able to be better than at least, so our requirement is to be 1/10 of 1 sigma accurate, and we're always better than that very often by a large margin. So this is one example, but CCL also implements a lot of other things. We have background quantities and linear growth quantities, power spectra that we can compute with different approaches, halo quantities, mass function bias, etc., concentration profiles, any halo model quantity, angular power spectra, and correlation functions for different combinations of galaxy clustering, cosmic shear, and CMB lensing, and 3D correlation functions as well. So there's a lot of stuff in there, but the code is still going to be evolving. We need to keep on increasing its capabilities. We want to make it more flexible. So we, for example, want to be able to pass generalized input power spectra that may be not physically motivated, but that we want to explore anyway, and also radial kernels for our Limber integrals. Other observables such as CMB secondary anisotropies like SZ and ISW, and implement generalized halo models, things like that. Optimize the speed of the library and integrate with other parts of the pipeline, in particular integrate CCL in the likelihood library for LSST. If you're in LSST and you want to do any work on any of this, particularly in this last part, everyone will be very thankful and cover you with praise. So I think I need to finish in 30 seconds. So there's one last project that I wanted to mention, but I'm not going to have time to do that. This is in this project, which we did with Darsh, and who is a student at Oxford, and Pedro Ferreira, also at Oxford. We looked at the effect of the parameter dependence in the covariance matrix. So when we need to evaluate this likelihood, we need to worry about whether or not the covariance also changes with parameters, or whether we have to recompute one covariance matrix at every point in the likelihood. So that would be bad news, but the good news is that blah, 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 it doesn't matter, okay? And you can go through the math and all that if you look at the paper. These are the conclusions, which I'm not going to read through, and thank you very much.
little bit of a question about the blah, blah, blah.
Yeah.
So it was very, very nice to... I haven't read your paper in detail yet, but your result is great. Makes everybody very happy. How does it compare to previous results by, for example, Dodelson and Schneider, who actually looked into parameter dependence of covariances and said it will be a problem?
So I would say what has been explored in previous papers, which is extremely relevant, is how much... So you have two different approaches, right? Either you vary your covariance matrix with parameters, or you just keep it fixed to some fiducial cosmology. What has been extensively, I think, tested is how close to the fiducial cosmology you have to be to avoid biasing your results, not whether or not you need to worry about the parameter dependence of it. And I think in that sense, we agree with those papers. Yeah. And since you've given me the chance to explain all the blah, 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 the idea is that the amount of information that is encoded in the mean increases much faster with the number of modes that you have in your data than the information encoded in the covariance matrix. So as long as you have a sufficiently large number of modes, you're always going to be dominated by the information in the theory, so you don't even need to worry about that. Something that is very nice is the HSC people in their analysis, their likelihood varied the covariance matrix at each point in the MCMC, and basically things don't change at all when they do that. So that's also a nice confirmation of that.
So, David, I have two questions. So, maybe I understood something wrong, but you're saying that at the beginning of pseudo-CL method, right? In general, it didn't work very well if your spectrum was, it changes very fast.
Yeah.
Right. The steeper it is, the worse it is.
Yes.
But then you went on to apply to the CMB and get nice results. So
yeah. So this is CMB.
Looks like really contradictory.
Yeah. No, that's a good question. I should have clarified. The CMB TT power spectrum is extremely steep because of the damping because of a lot of reasons. What this can be very useful for is B modes. The B mode power spectrum is either noise dominated because you have been able to delens a lot. And if it's noise dominated, then this is fine. So pseudo-CL is a good algorithm. Either it's that or it's dominated by lensing B modes. And the lensing B modes at low L is an extremely flat power spectrum. So in which case the pseudo-CL algorithm also works.
The E modes also are flatter, right? The E modes don't change so fast.
The E modes don't change. That is true. As long as you use...
useful for the E modes?
So it's useful at high L. At high L, you can still do quite well with the pseudo-CL, and that's what people actually do because it's impossible to implement a maximum likelihood estimator in that case. I think that's all I want to say.
And the second question is, you're right. You say most of the information now we think is in the power spectrum because things are very Gaussian, but we do have very important information outside the power spectrum. Lensing, for instance, introduces correlation. So is it useful at all to do something similar to this if you want to get, for instance, the lensing of the CMB, or no, you have to start from scratch? And
say that, no, I don't understand.
Like lensing effects go outside the power spectrum, right?
For CMB, for example, you're talking about, yes.
Yeah. So you have lensing effects. We have high order. It's
a 4-point function kind of thing.
You have aberration effects also beyond the power spectrum. So can you use something similar in these cases? Or
I haven't thought too much about higher order statistics, to be honest. I think so. Antonino actually is someone who has worked on higher statistics. He might know more than me about this. So maybe you guys want to talk later. Yeah. No.
Questions? More questions? Okay, let's thank David again.
Just
Does it only?
okay.
The next talk It's given by Domenico Sapone. Internal robustness, of growth data.
Okay, thank you so much. Well, I will be talking about this method, how to verify whether the growth data that we have at the moment are internally robust. So basically, answering the questions whether we can still use to infer cosmology or not. A little bit of introduction. So this is the general picture that we have in the kind of universe we're living, which is composed by 90% of unknown stuff. And the goal of the cosmologists is to understand what this 95% is. And so how did it come, these measurements? So by measuring stuff. So when we want to measure in cosmology dark stuff, what we really, this is the pointer, I think, right? Yes. So what we have basically is, if we assume the GR is the theory of the dynamic of the universe, so what we measure is the geometry of our universe. So we have a phenomenon which is whatever, supernova or galaxy clustering, and our galaxy. So the light starts from this something, then it travels over space-time, and then it finds something in between. And of course, our measurement is affected by this something in between, and this something is our geometry, and which is determined in terminology by the metric. However, this geometry is strictly connected to the amount of stuff we have in our universe. So now this little game actually led to the conclusion that in principle, so what we have to do in the real cosmology is to consider the total amount of energy momentum tensor, and which means also that we can parameterize whatever modified gravity model we have in terms of fluids, like dark matter fluid and also dark energy fluids. Sorry for my... So as I said, okay, now since we are observing something, and this something, of course, which is the geometry it depends on the geometry, depends on the amount of energy momentum tensor we have in our universe. So the amount, which is parameterized characteristic of this fluid itself. And so we measure basically distances. Up to now, mostly we measure distances. There are functions, depending on the kind of distance we have, of this dynamic of our universe. And then, by measuring these distances, we have the constraints that we usually have in cosmology. So this is the picture, which I didn't update because basically here is the evidence of measurements coming basically only from measuring distances, not supernova luminosity distance, BAO, the angular diameter distance, and also CMB, it's the distance at less scattering. Okay, so we arrived to a point where, okay, we live in a universe with dark energy, something that is dark energy, which is the 70% of the total budget of a universe, and of course we want to find the theory behind this acceleration. Well, we have different approach nowadays, which is, okay, either you put a fluid or you modify gravity, as I said. Okay, the two can be actually parameterized in the same way. Or also, for instance, the new ones are these, well, not really new ones, but okay, non-homogeneous models also can be taken into account. Of course, okay, these models are really complicated, and so progresses haven't really been done nowadays. Anyway, so our question is, what do we have? So we have different approaches actually to explain the same thing, because we want to explain what is the acceleration of our universe, who's responsible. And of course we want to know which one is the real one, so the real model. And we have to ask also, what do we need to do? Well, there are several things. This last question actually comes at the end of my talk, not now. But okay, and we want to ask ourselves if all these methods are reliable, and also, for instance, if we can find something else which can speed up or can actually help us to remove one of the approaches that we have. Okay, the thing that we actually do at the moment, well, you all know, is what? Okay, you have your data, you have your model, you put everything in a magic box, which is the chi-square, right? and then you verify whether the data confirm the model or not. If it's not, you introduce another model. If it is confirmed, okay, you cross-check with other data, and then, okay, you put again everything in the magic box, and you verify whether it is confirmed or not. And then, okay, you might have that, okay, different models might be confirmed by the data. And then, okay, using a Bayesian statistics, you can say which one is the most favored one. And this is all the machinery that we have, that we use nowadays. And then we will see, okay, later also a different approach of this method. Okay, so the data that we have are divided into 2 different categories: geometry data, which are the measurement of the Hubble parameter, the angular diameter distance, and distances in general, and also gravity data, which measure the growth of the structure that we have today, which basically says the geometry data depend on only on time, so it's the density that changes over time only. And okay, as we said before, the density, if it changes also the distances. Whereas the growth data is basically was the perturbation that you add to your background, and you study the evolution of this perturbation. And of course, okay, our data basically will be this part here, the data that we consider now. So usually, okay, as we said, you have your theory, and well, you use your theory, Einstein or not, or whatever you like, and then you evaluate what it is, the evolution equation for this density contrast, so the growth of matter. And of course, okay, this is another differential equation with functions here, and all these functions are very complicated function of time and space, and depend on which model you're using, and so on and so forth. Anyway, so once you choose your model, okay, you also define these functions. However, the data, well, observation do not really measure delta itself, but they measure the so-called F sigma 8, so the growth rate of structure times this root mean square density fluctuations. So you can express in terms of the different function. This is the growth rate, which is the delta prime, so the derivative of delta, how fast delta grows over time, and then you have your sigma 8, root mean square density fluctuations, and you end up with these quantities. These are our data, and this is also our theory. Okay. And these are the data that we have now. Okay, basically here, this is a plot, courtesy by Savannesteris. So here are the data that we're using, and here of course, what he did actually, was to try to fit different parameterization, but different models. For instance, lambda dark matter, one modified gravity, FOVR gravity theory. So okay, well, and basically now you can fit everything on these data. You can sort of rely on the chi-square, but of course in a fully Bayesian way, the chi-square is not enough actually to verify whether a model is accepted or not. You should evaluate all the likelihood function, the integral of the likelihood, so which is called the posterior. These are the data that we're going to use in our analysis. What we want to study is whether all this data here are robust internally. Why that? Because all these data come from different experiments. As you can see here, you can't. But anyway, so, and then one question is whether, since they come from different experiments, of course, different experiments might have different systematics, and we want to be sure that before invoking new physics, so the data actually don't have something weird inside. Okay. Because a set of data, for instance, might follow in principle one physics, and the other set another physics. So yes, and the idea is to verify whether we can use safely this set. In our analysis, our data will be modified according to this factor, which is sort of Alcobaginski effect, which comes from the amplification of the volume when you consider different cosmology. And in fact, this data have been evaluated according to some cosmological model as reference. And then when you do, of course, a Monte Carlo analysis, this model will change, and of course will change the Alcobaginski effect. And so this will be taken into account in our analysis. Again, why we want to study the robustness of this data? Again, because first of all, okay, they come from different experiments, and also because of the tension that we saw so far. No, in all the talks, we saw this plot, actually a more updated version of this. And so, again, before inventing a new model that helps you, like solve the tension, so to bring down, for instance, the value of sigma A to the value measured by Planck, from the local measurements to the value measured by Planck. So, okay, it's safe to ask if these data that we have are safe. Okay, you all know probably statistics. For those who don't, a little summary. So we have three definitions basically of probabilities. So the frequencies approach, which is a long-term frequency, it's called, and the idea behind the frequencies is that you are not able to do anything else but counting events. Counting events, and then, okay, divided by the number of events, and then you have the frequency of something that can happen. Instead, okay, the Bayesian approach, okay, it's sort of, it is a degree of belief of your analysis. The main difference that comes here is that, first of all, if you use the Bayesian statistic to play with uncertainties, things that you cannot do actually with the frequencies approach. And for instance, as I said before, if you want to value the mean of something, in the frequency approach, the only thing that you can do is to count events. Instead, in the Bayesian approach, you actually play with the uncertainty of this mean and update the probability again and again and again according to the new experiments. And actually, this is what we do in everyday life. So actually, we are intrinsically Bayesian because, one example that I always do is that when you want to know the probability, if you die if you cross the road, and then okay, some people might say, okay, the probability that you die if you cross the road is, I don't know, 0.2%, because someone previously counted how many people died crossing the road. But then, okay, the statistic might change, it might be a little bit more complicated, and saying, okay, but there's a car that is speeding, that is traveling at 80 kilometers per hour. So now the statistic will change. And so this you have to take into account. And this you can do only if you use a Bayesian approach. Or you wait for someone that counts all the possible events, and then it will tell you the probability. And then so on and so forth. So, the Bayesian approach actually is always something that updates itself. Plus, also it's a statistic that it's valid if you have only one experiment, which is our universe. Anyway, so our analysis, why I'm saying that? Because our analysis is based on a fully Bayesian approach. So which is, okay, as I was saying before, the prior probability is the information that you previously have from someone. In our case, for instance, the 0.2% probability that you die when you cross the road. And then, okay, this is the so-called likelihood, which is the conditional probability of having an event if something has happened. Okay? And divided by what is called evidence, which is the integral over all the possible events that can happen. And then you find the posterior, okay? And which, of course, the likelihood that you have will be affected by the information of the priors you use. Okay, let's go now to the details of the method. Okay, this statistical method was introduced by Amendola, Marra, and Miguel, was here in the 2012. And so what we use now is statistical evidence, which is basically the integral of your likelihood function over all the parameter of the model. So here we have the likelihood, which is the data given the parameters. And so you integrate, this is the full evidence of one particular model M. And then you want to evaluate the posterior. The posterior is just the evidence, so the likelihood that we had before, and multiply by, the prior of the model and the prior of your data. Okay, now with this, actually we can compare different models just by the ratio of the two posterior function. And then we have, okay, since the priors of the data are the same, so we have this factor B1, 2, which is called the bias factor. It's just the ratio of the two evidences of the two different models, and of course the ratio of the priors of the model itself. And now our idea was not to evaluate the evidence of different models, but rather to evaluate the evidence of one model that comes from two different data sets. Okay? So basically we are dividing the evidence in two factors. So we factorize the bias factor in one term, which is okay, the evidence of one model that comes from one data set, and the other one that comes from a different data set, X2. So what we will do is to take the data, we do the partition of the data, now we will see, and evaluate the evidence of one particular model, which is lambda quadrata dBg, and evaluate this ratio. And according to the value that we have, okay, we can say, okay, we have inconclusive evidence or not. Okay. So we need a model to evaluate the chi-square, so the likelihood that we choose lambda quadrata. This is one. Why? Because okay, it has only parameters and has density and sigma is 0. And of course we need priors for these two parameters, as we said. And so we choose okay, omega from omega matter. We use a flat prior, so it's easy that. Instead, for sigma 8, we chose three different ones. So narrow flat, or flat but broader, and a Gaussian prior around the Planck, the best fit of Planck. And yes, and we create different partitions of the data. So if evaluating the internal robustness of this data, we might conclude, depending on the outcome, that okay, different subsets of this data follow different physics. It might be, or if you consider two models, no, even if two models are the same one, and then okay, or if there are systematic errors in the data, or simply outliers, so data that shouldn't be there, but they are. The problem is that okay, as you will see, we have 22 data, and since we want to partition this data, we have like 2 million, different combinations. So what we do is that, okay, we have these 22 data, and we take one, for instance, the first one, and we put it in one box, and then all the rest in another box. Or we take another configuration is that, okay, we take two data, we put in a box, and the other one we have 20 data. So we have all the possible combinations, and yes, okay, the problem is that, okay, we have too many combinations, but luckily for us, since we are considering lambda quadrata matter, and we have only two parameters, and sigma 8, 0 enters in a nice way in the equations as a multiplicative factor, so we can actually marginalize analytically. And also we have, at the end, a probability distribution a posterior, which is fully analytically, so we don't have to do any integration. Only for this case, because if we had a different model, which was more complicated, maybe, okay, this is not the case. Okay, and these are the results of internal robustness. And these are called violin plots, because they look like violins. And so here, as I was saying, we show the SSS, which is the smallest subset of data. So here we take one data, and put in a box, and all the rest in another box. Here we take two data, and we put in the box, all the rest, the 20 data in a box, and so on and so forth, up to arrive at 11. And so the values that we obtain from this partitioning show that that we don't have weird stuff. Okay, I cannot point. So we don't have data that are strange in our data. So we can use basically safe all the data we have. Why that? Because the internal robustness is a value that is actually larger, not than 1, and we don't have values smaller, so which might point out to the fact that okay, some data shouldn't be there. And as we increase the subset, so as we increase like okay, we put in one box more data, of course, internal robustness increases, which is logic to think about because, okay, if we have more data in one box, okay, all this set will confirm something, and this was used, this was evaluated using, I didn't write it here, was the narrow flat prior. Also, we tested with different priors, the broad one and the Gaussian one, and we don't see any weird behaviors in the data. So at the end of the day, the data set that we're using is safe. We can do cosmology with that, even if they come from different experiments. And of course, okay, if we use a broader, not prior for sigma 8, the value in principle of internal robustness increases, which makes sense because, okay, we allow sigma 8 to vary freely, no more freely into the parameter space. And instead of using the Gaussian prior for sigma 8, okay, the internal robustness stays a little bit lower, and because of course we are forcing the value to be one in particular. Then at some point we asked ourselves whether this method was sensitive. Well, before doing that, okay, when you check data and you have a method, what you have to do is also to do a blind, well, not a blind, it's a controlled experiment. So what we did also was to evaluate the probability distribution function of this internal robustness using MOX catalogs. And we did 1,000 catalogs. So in each catalog contained 14,000 points, 5 sigma 8, with the same errors of the data and with the same fluctuations of the data. The MOX were evaluated around the lambda matter model, and here we plot the probability distribution function. So, and here we have, okay, the value that we saw before in the plot. So the internal robustness of the data is more or less 3. This is for flat, narrow, prior sigma 8. And the blue shaded ears are from the MOX. And we see that, okay, first of all, that the model we were using to test the data is actually safe also, because at some point we asked, okay, maybe we are obtaining this because the lambda model we were using was too simple, and then say, okay, let's evaluate the full probability. Okay, so, and well, the data actually fall inside well within almost the 1 sigma. Well, this is 2 sigma, the light blue. So the model also that we were using, so doesn't affect actually the results. And then, okay, we asked ourselves whether this method we were using was sensitive to the data. So what we did was, okay, to contaminate the data. So we took one random data into the catalog, and we moved 5 sigma away from the actual position. And actually, we see that the method is really sensitive. So here we have, okay, the mean, let's say, internal robustness, but of course now we have a tail of -15. So the method was telling us, look, there's a point there, no? Because here, okay, the lowest one is at 1 SSS, so smallest subset data. Then it has an internal robustness of -15. So something weird is there, no? So watch out. And instead, if we increase, of course, okay, this ER increase a little bit more. So, and also, okay, again, we evaluated the full probability distribution to verify whether, okay, the model is also safe to consider. And also, we see this weird tail from the data. So, our final result is that data are safe, and the method actually is really safe and powerful. And the problem is that, okay, it's really time consuming, as Miguel actually can tell you more deeply on that. Yeah. And but bottom line, okay, this data that we use, we can do cosmology at least, no? Even if we have only 22 data. Now, very fast, I want to mention something that, at the beginning I said, okay, what do we need to do? No, so I showed like a chart flow of the magic box we were using, but then, okay, our question is, since we have too many models, maybe we can think of something a little bit more, you know, not wise, but I mean, something different, not whether instead of doing all the MCMC for different models, maybe we can think of something more faster. So over the years, there have been an increased interest on finding the model-independent test. And the idea behind this is that, okay, you have a theory, no? You choose whatever model you have, and you choose a function of the model, which characterizes the dynamic, of course, of this model. And then you rewrite this function in another term, in another way, that depends directly on the data. And you want to manipulate this function to be equal to a constant. Then, okay, you put the data into the function that you have, and you verify the constant. So if you get the same constant, well, the data confirm the model. If it's different, okay, the data says something else. And this something else is what? That, okay, maybe the model is not the correct one, maybe there are tensions in the data, maybe something else. One example is this statistic, so to show you how it is. So you have your Hubble parameter in this lambda dark matter model flat also. And the statistic is to evaluate omega matter in terms of your direct data, which is the Hubble parameter. Okay? And then you put here the Hubble parameter, the data that you have, you verify whether omega matter should be constant, because in principle in the lambda dark matter cosmology, omega has to be constant. Okay, 0.3 over all the redshifts. If you measure something else, then okay, something happens, something might happen, either the data or the model. And what I did with also what I did with Savas, the series, is to find a new null test considering the growth of data. So how we do that? Very fast. So we have our model, we chose lambda dark matter. So we have delta, which is the growth of matter, which has this particular expression, and then we wanted to find, wanted to write it in terms of as a function of the data. And data will be okay h, and I will see sigma h. How do we do that? Okay, we use the Lagrangian formalism. Okay, we use classical mechanics. Actually, giving course undergrad students help you doing some research. So, and then you have, okay, here the Lagrangian has what? The scale factor A, which will be our time, delta, which will be our position, and delta prime will be our velocities. And so what you want to find is actually the conserved quantity of your dynamic. How you do that? With your Lagrangian equation. So you find your Lagrangian. It's a fictional Lagrangian, it's not a real one. No, it's just this is a mathematical method that we use to find the conserved quantity. And with the help of another theory, well, okay, and the Lagrangian has to be what? Okay, has to depend on the velocity square, on the position square. So you plug into the Lagrangian equation, you evaluate, then you compare with your master equation of the density constant, and you end up with this expression, which is one particular kind. And once you have that theorem, you find your conserved quantity, and which we found to be this capital sigma, and which is constant. So we did the calculation correctly. Of course, as I said before, we don't measure delta, but instead f sigma h. So we have to translate that capital sigma into well, as a function of Hubble parameter h and f sigma h, and we end up with this expression, which may look weird, but well, this is what we have. And once you have that, since now we confirm that the data we are using are, we can evaluate actually this null test. So in principle, if lambda dark matter cosmology is the correct model in our universe, so this O should be 1, okay, over all the redshift. If we measure something else over the redshift, then it's not lambda. And we might have that, okay, there might be dark energy perturbations, or there's a modification of gravity, or we're living in a universe which is not homogeneous, or we have tensions in the data. But now we saw that tension we don't have anymore. And these are the results. You can do different stuff. You can beam directly the data. Okay, sorry for this plot. This hasn't been updated since the last one, so we have a redshift only up to 0.8. And so there's nothing actually, so beaming here matters because we have few datas. Here we had 16 instead of 22. So in fact, if you consider 4 beams, so you might measure some deviation from lambda dark matter, but then if you do use 3, okay, everything consistent with lambda dark matter. And also you can do other stuff more sophisticated, like, okay, evaluating this function O, or NS as it is here, with the linear formalism, which is an analytic approach to construct your functions. And still, okay, within the errors, so well, lambda dark matter seems to be consistent, so nothing strange is happening. Here we're using different a value of sigma x 0, which might change the position, but still within the errors that we have now, we don't see so many new physics, let's say. And it's that, and so before, for instance, we invoking new physics, we have to make sure that the data we're using are consistent, not within internally consistent. And as I said, the method use is very strong, powerful. Was been originally checked with the supernova, and well, it's too demanding computationally, and yes, and that's that basically.
Questions?
I'm new to these violin plots, so I just want to sort of check I've got the intuition of them right. And in particular, the changes you see going from left to right. So am I then right in thinking if you have something that is genuinely inconsistent, what you're supposed to see is that something that is genuinely inconsistent in your data set, that what you're going to see left to right is that the tail persists. And if your data is not really inconsistent, it's just got some acceptable fluctuations in, the tail is going to kind of rise as you go towards higher values of your triple S.
Okay, if you move to the right, so imagine you have one data, as I showed before, that it's just shouldn't be there, okay, and it's wrong. And you have to see the tail that is increasing. So the value has to go really down.
Yeah.
Okay. So as you can see, if I increase SSS, so this tail is decreasing a little bit because it's somehow here we're considering more data in one box. So in a way, sort of averaging all the possible contaminations, right? So, and then, if you consider 11 data points in one box, then, all this set is sort of okay, because you're averaging. So in principle, as you increase, you have to have more consistency, let's say. So so here basically either a large number of data, like imagine 11, among 11, 5, or if it's only one, then you should see more effects for lower triple S. I don't know if I answered your question.
I guess what I'm just trying to get a handle on is what I should be looking for in this kind of sweep that says everything's okay, or there is a problem.
Okay, in this particular case, there's a problem because you have this weird tail.
Because the tail persists.
Exactly.
Span. Whereas if everything is okay, can we flick to a different plot, then the tail
Was okay?
Yeah.
This one, for instance, yes.
So these still have a tail, but so like the bottom one going down to -2, there's a tail that forms there, but that isn't. Why is that not a problem?
Because basically it goes up to only -2, let's say, but all the bunch stuff, it's up here. And then, this means that if I consider this 11, consider that this is not one only configuration. So it's like, among all the 22 data, I take all the possible combination and I put all the possible combination in one box of this 11 data. So among all these possible combinations, there's one or two, let's say, that is particularly weird. Okay? But then, when you go, so then why it's not really a problem, this one? Because when you consider only a box with one data only, here you don't see any value that goes really down to -2. Okay? So it's like, singularly, the data do not show any inconsistency. But then, when you put like in 11, in a subset of 11, there's one data that doesn't really follow as I should, but okay. But if this had something like this, then also in this case would have been a problem.
Okay. All right, thank you. They're nice plots. It's just learning how to read them.
Yes.
Yeah.
So, Domenico, I have a question, and maybe we'll clarify a little bit this question. There was can you put it on the next plot? The next one, I think, is easier to. So when we.
This one or the other one?
Well, the one which is wrong for sure. When
this one.
This one. It's just okay. So the thing we had more, was less clear for us when we were doing this method originally is just like, okay, once you have this plot, how do you quantify, the deviation, right? So the way we solved it was by binning in bins of internal robustness, right?
Mm-hmm.
Binning and did you bin as well? How did you compute this in the end? Because in the end we had to bin in different internal robustness compared to the mocks, and then see how much each bin was unlikely, and then get a final result, a number, right? Mm-hmm. How well do you agree or not? Did you bin in internal robustness, or how did you solve this?
I mean, I don't know if I get the question. So when I do the mocks.
No, in the end, we get this plot. That's your final result,
okay.
Right? Do you get a number out? I mean, how bad are you fitting overall? I think it's a little bit her
yes,
question.
you get a number for this.
Yeah.
Okay, yes.
Okay, how do you translate this plot in a number? Did you try to do this or not?
Okay, no, you have you have the value of internal robustness, so that one you can see there, for instance. And then, you have, so this shaded area is what the errors given by the parameters that you're using. Okay, so you have an error also on internal robustness itself, and this is what we evaluated. So we gave this number.
So you did not have to bin this plot for the analysis. Okay.
No, it's just fully there.
More questions? So thanks again, Domenico. Now it's lunchtime. Please be here for 2 p.m.
Io che se ne accorta di tu, non sapevo.
Can you just walk there? Yeah. Okay. Yeah, I can sit wherever you this. I'll Elizabeth. Okay.
So I lock the auditorium. You can leave your stuff here.